And welcome back to another LeetCode video. Today we're looking at LeetCode 3712, sum of elements with frequency divisible by k. I have not solved this problem before, and I'm using, these problems to practice the interview process and to practice speaking while I code and explaining what I'm doing. If you're looking for an explanation, well, I guess the easy problems are easy enough to get an explanation out of those videos here. But just keep in mind, the main purpose is really to be thorough with how we approach the problem, and as we would in a coding interview. So let's dive into it and start with understanding what this problem is about. So we are given an integer array nums and an integer k, right? And we should return an integer denoting the sum of all elements in nums, whose frequency is divisible by k, or 0 if there are no such elements. All right, so we probably have to check every single element. Is it divisible by k? If so, we add it to our sum. Nice. Note, an element is included in the sum exactly as many times as it appears in the array if its total frequency is divisible by k. Oh, wait. So I misunderstood. So the frequency of the occurrence of an element in nums must be divisible by k. Aha, okay, nice. All right, so next question would be, what are the constraints? Can nums point to nil? Can it be an empty array? Are we guaranteed that there's always one number in there? Are these all positive numbers? What's going on? And in LeetCode, the constraints are listed below. In an interview, you would ask that the interviewer. So we're guaranteed to have at least one number in our array, and all numbers are going to be positive and larger than 0. And same for our k values, also going to be larger or equal than 0. By the way, we don't care about the upper bounds, otherwise the runtime complexity analysis would be well, pointless, right? Those things would be O of 1 if we had an upper bound on the length of the input, for example. Cool. So here's an example. So the third step is now looking at the examples. And yeah, and let's just see if we can solve this by hand, right? So we have, so here it's in sorted order. Here's not in sorted order. So the nums array is not always in sorted order. That's all right. And here we have now, yeah, that's actually also a question if you should ask the interviewer, are the numbers sorted? Because when they're sorted, I think we could exploit the fact that they are sorted and get away with less space to use. But anyways, I will maybe I'll explain this later. So okay, so now we have, and what is k? Well, k is 2 in this example. Hang on, k equals 2. So 1 occurs only once, so that's not an option. So we can forget about 1. 2 appears exactly twice, so 2 has to be added to our sum, right? Because it occurs twice. Now 3 occurs 4 times, which is divisible by k. So we have to add 3. But do we add in all elements and nums, blah, blah, blah? An element is included in the sum exactly as many times as it appears in the array. So we have to include 2 times 2 and 4 times 3. And 4 is only once inside the array, so it doesn't meet the frequency requirements. So our result would then be 12 plus 4, so that will be 16. And that is actually the output. Nice, cool. I think we've understood the principle. So now what we can do is we can sort the array. So I see 2 different approaches. I see one where we sort the array and then we have n log n time, and we can get away with constant space. The other approach is where we have O of n time and space, where we use a hash map to compute the frequency of the elements before we iterate over them. And so when you have a scenario like this, you can explain the solutions. The first one would be, okay, we sort the numbers in order. And then we just have to keep track how many times we encounter the current element. And once we encounter a different element, we check if the frequency of the previous element was divisible by k. If it was, then we add that to our sum. Otherwise, we just continue. So that's why we would get away with constant space. And the other approach is to say, okay, we're going to iterate over all of the numbers, determine the frequencies, and then iterate over all of the numbers in our hash set again and pick out those that have the required frequency. So I think we should implement both approaches, just to show you. And so let's implement the linear time and linear space one first? Well, we're going to use a little hash map for the frequency, right? And we could call this frequency. I'm just going to use a default dict that makes it easier to initialize it. And then we just iterate over the numbers for n in nums. And we're going to say the frequency of a number is going to be increased by 1 every time we encounter it. Now, finally, what do we need to do now? Well, now we need to iterate over all of the distinct numbers. So for n in frequency, or we could just do iterate over the numbers and their frequency. I think items is the correct way to do that. So now we get the key and the value out of the dictionary. And we say if frequency divisible by k, right? If we divide frequency by k, then the rest should be 0. So frequency modulo k should be 0. Then we're going to add the number times its frequency to our result sum. Return a result at the end. Now we should return 0 if there's no such element, right? So we achieve that by initializing our result with 0 in the beginning. And so that, I think, is everything we need for the first implementation. So let's just run it through the tests to see if that works. And that works. Now we submit it to make sure it really works. Kaboom, it works. Great. So now let's implement the other approach just to show how, just to see how that works. Right. So, well, we're going to sort our numbers, nums.sort. Now sorting is done. Right. So what do we do now? Well, we iterate over nums for n in num. And we're going to keep track of the previous number. And we also need to keep track of the current frequency, right? Current or frequency. Maybe we call it previous frequency. I don't know, or current, or just frequency. Let's just call it frequency. So now if, well, we have to do a case. If previous number, n, is none, I guess we have to skip that or so. But let's think about this in a second. Forgot to put my result in here and to return it here. So what we will do now is we will, well, every time n is equal to the previous n, if n equals to if n, we're going to increase the frequency, right? And only when it's not the case, then that means we have to add, well, we have to do a check. If frequency modulo k is equal 0, then we need to add to our result frequency times previous n. And we have to reset our frequency to 0. Well, actually, we have to reset it to 1, right? Because we now just encountered the next number. And at the very end, what we will do, we have to check, you know, what is the frequency and what is previous n, right? So we will do this check one more time at the very end. Yes. Otherwise, we might lose out on, you know, because we perform this check if the frequency is only when counted a new number, but not at the very end in case we didn't account a new number. So if the array here would end before the 4, you know, we'd have a frequency of 4. Previous value would be 3, current value would be 3. So we would never trigger this case. We have to do it after the loop. Now let's try to simplify this a little bit. So I think we can say we have to increase the frequency anyways, always, right? So if, actually we could do, so if n is not the previous, is not same as the previous number, then we perform the check, is the frequency modulo k equals 0? Then we're going to add something to the result and we're going to reset the frequency, right? And now let's examine the case where previous n is none, right? In the first iteration. So this would be true. We would actually also compute frequency. frequency module k is also going to be 0. However, 0 times none, well, okay, that would be an error now, because we can't multiply with none. So we have to do if prev n, and have to perform a check that prev n is not none. I think that is all we need. So let's just run this through the test cases. See if we spotted, if we missed any obvious errors. We're getting a wrong result, so something is off. Initial frequency is that. So we're getting 0. In this case, we're getting 0. Oh, we're not setting previous n. Okay, that's of course stupid, right? So we have to set what the previous number is. We don't only have to set it in here, we can just set it always. Doesn't change anything. Try again. Okay, so we have one test case that passes where we expect 0. And here it doesn't pass. Where prev n is not none. Because if, can we have a 0 in here? No, we can't. So this doesn't matter, but this is probably better. If prev n is not none and n is unequal to the n, then we check the frequency divisible by k. If it's not divisible by k, we don't add anything to the result. Otherwise, we add the frequency and the previous n to the result. Then say frequency 1. No, this is the next mistake. We have to say it's +1, not 1. So that's just a reminder why you should always go through your code with an example. Here, I don't know if you can tell, but I kind of want to speed run this a little bit. In an interview, that's not a good idea. You should really take the time to go through your code step by step with an example, and then you spot these things right away and not just when you know that something. So the test case is passed now. So now I'm going to submit it to see if it really passes all the test cases. And it does. Very nice. So what you've seen are 2 approaches, and you've seen how you can explain 2 approaches before you write any code. And typically you would ask the interviewer which one they would like you to implement, or if you have a preference, just say, if it's okay with you, I would implement this one first. You know, the linear time one is the one that's easier to implement. The other one has a little bit more if-else shenanigans, right? Try to go with the simplest one to get easy points quickly. You don't want to get tangled up in things where you need to start to debug stuff.